Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is July 11, 2016. In this video lecture, we are going to discuss the law of conservation of momentum. The law of conservation of momentum is one of the most powerful laws in physics. The law of conservation of momentum states that the total momentum regarding masses interacting with each other remains constant. Momentum is defined as a mass of an object times its velocity, which equals mass in motion. The law of conservation of momentum is defined by two or more masses in motion which interact with each other by the formulation of mass 1 times its velocity plus mass 2 times its velocity, and so on, when added together has a total net momentum which equals 0. Neither momentum is gained nor lost but conserved within the system of interacting masses. The best way to explain the law of conservation of momentum is by examples that take place every day in the real world. So I put together a series of examples which reflect on the law of conservation of momentum. First example, a spring-loaded launcher accelerates a 2-pound object from rest to 20 feet per second final velocity. After the acceleration, the launched object exhibits a momentum of 2 pounds times 20 feet per second, or a momentum of 40 foot-pounds per second. If the launcher weighs 10 pounds, this means it will absorb a reactionary momentum equal to that of the object launched, or 20 foot-pounds per second momentum of the object divided by the 10-pound launcher equals 2 feet per second of velocity will instantly transfer to the launcher in the opposite direction of the launched object if the launcher was not firmly fastened to whatever it is resting on. This perfectly demonstrates that the momentum is neither gained or lost in this particular system, but is conserved between the launched object and the object that launched it, the launcher itself. It could be said that the law of conservation of momentum is an observation reflecting upon at least Newton's second and third laws of motion, to a lesser extent perhaps even Newton's first law of motion, especially collisions opposing an object in motion, could also reflect upon the law of conservation of momentum. As for an object at rest with no momentum set into momentum by an object that collides with it, losing its momentum and transferring it to the object at rest, causing it to move into a momentum, is also a reflection of the law of conservation of momentum. If one thinks about it, all of Newton's 3 laws of motion do in fact reflect upon the law of conservation of momentum. Next example, a jet engine accelerates 500 pounds of mass air to a final velocity of 900 feet per second out of its exhaust nozzle and is attached to a 3,000-pound airplane. The momentum of the mass air accelerated by the jet engine will induce a propulsive momentum of 500 pounds times 900 feet per second, or 450 foot-pounds per second of momentum. Since the jet engine is attached to a 3,000-pound airplane, the 450,000 foot-pounds per second of propulsive momentum will become conserved as reactionary momentum in the opposite direction upon the 3,000-pound airplane, resulting in velocity to the airplane in the opposite direction of the mass airflow momentum equal to 450,000 foot-pounds per second divided into 3,000-pound airplane equals 150 second speed transferred to the airplane in the opposite direction of the propulsive momentum. The maximum speed of this airplane could travel with the given propulsive momentum is 150 feet per second in the opposite direction ignoring aerodynamic drag and tire rolling resistance if airplane is on the ground, provided the momentum of propulsion was maintained at a constant output. Next example. A rocket operating in a vacuum carries its own liquid hydrogen and liquid oxygen gas producer system mixed with aluminum slag for adding enough weight to the oxyhydro combustion jet velocity, which first accumulates into a diffuser into constant pressure. Then it is stepped down from pressure to velocity by a convergent nozzle for the rocket's exhaust attached to the end of the diffuser. Since this rocket carries its own oxygen and combustible fuel, it does not require an atmosphere for combustion. There is no air or atmosphere, yet the rocket develops excellent thrust, push forward of the rocket. Some might wonder why this is so. It is due to the law of conservation of momentum. That is because the exhaust velocity of the rocket is a product of mass gas acceleration to a final velocity, allowing the expelled rocket thrust gases to exhibit momentum. The rocket itself then absorbs the positive momentum of the thrust momentum onto itself as negative momentum equal to the momentum of the thrust gas divided into the mass of the rocket, leaving only a certain forward speed for the rocket to absorb. An example of this is defined by, let's say you have a rocket thrust momentum of 30,000 kilograms of exhaust gas times 2,500 meters per second rocket jet velocity. So when we multiply those two out, that's 75 million kilogram meters per second of momentum. The rocket mass is 50,000 kilograms. So when we divide the 75 million kilogram meters per second of thrust momentum into the mass of the rocket, 50,000 kilograms, that translates to a rocket forward speed of 1,500 meters per second. Rocket will reach final speed of 1,500 meters per second if the rocket thrust momentum is continual. All of these examples clearly prove that momentum is conserved in regards to any system of motion for which mass is in motion. Next example. A cannon fires a 50-pound projectile to a final speed of 400 feet per second. Assume that the cannon is not properly fastened to the surface it is resting on, and the cannon weighs 500 pounds. How much speed in the opposite direction of the projectile's motion will the cannon instantly accelerate to? Well, you have a 50-pound projectile times the final velocity speed of 400 feet per second. So multiplied out, that's 20,000 foot-pounds per second of momentum. The projectile exhibits a momentum of 20,000 foot-pounds per second by the computation of mass 1 times mass 1 times velocity 1. So that then applied to the mass of the cannon, so 20,000 foot-pounds per second divided by a 500-pound cannon translates to 40 feet per second. The cannon will instantly accelerate to a speed of 40 feet per second, ignoring the surface friction, if not firmly fastened to the surface that it is resting on when this projectile is fired. Again, this is a perfect example of the conservation of momentum. Again, this is a perfect example of the conservation of momentum whenever two or more masses in motion interact with each other. The total momentum between the masses are conserved and are neither lost nor gained, but are simply transferred proportionally amongst each other. Another example. Simple example most everyone experiences every day regarding the law of conservation of momentum is when someone tries to pull a pen cap apart from the end of a pen that is firmly stuck to it. As the tension to pull the pen cap off increases while holding the pen itself, when the pen cap breaks away, even though more tension was placed on the pen cap than the pen itself, the pen will move in the opposite direction of the pen cap proportionally to the momentum of the pen cap divided into the mass of the pen itself, causing speed of the pen in the opposite direction. Another everyday example of the law of conservation of momentum is when someone opens a door. the momentum of the door, mass times velocity, will transfer to the person opening the door, divided into the weight of the person, and result in speed of the person in the opposite direction of the speed of the door if the person does not brace themselves hard enough to prevent becoming moved to that speed. The law of conservation of momentum is a valuable tool for those involved in the physical sciences, especially when making analysis regarding machinery, solving technical problems, preventing problems from occurring by awareness of the law of conservation of momentum in regards to interacting masses in motion. One last example of the value of understanding the law of conservation of momentum would be a driveline on a machine which exhibits both linear and rotational mass in motion will become realized that the linear and angular masses in motion will not lose momentum but conserve their momentum as reactionary momentum to the frame they are attached to. Perhaps the technician, welder, or machinist involved with this particular driveline will take into account the framing and allow for enough frame mass and fastening to hold up to the reactionary momentum, thus preventing the frame from going into motion and causing a failure by, let's say, reinforcement welding with additional mass sufficient to hold up to the driveline's reactionary momentum. So again, the law of conservation of momentum is defined as two or more masses interacting with each other in motion. When added together, the total momentum will neither be lost or gained, but will equal zero. Thank you for watching this video, and have a great day.